Okay, good news. I accidentally printed in color this time, so we have a color page. Let's look at an example of an upper triangular matrix and a lower triangular matrix, just to finish off the definition we just did on the last page. So this is an example of an upper triangular matrix. And why is that? Well, just take a look at the previous page. What was the definition? Well, a square matrix is said to be upper triangular if and only if all of the non-zero entries, or any non-zero entries that it has, are either on or above the main diagonal. And you can see that's the case, right? All the non-zero entries are up in the top half. If I cut it across diagonal like a sandwich, and cut it across here, I go right along the main diagonal, it's the top half that is allowed to have non-zero entries. They don't all have to be non-zero, right? Here's 0 and here's 0. That's okay. In fact, they could all be 0. But what does matter is you're not allowed to have any non-zero entries down here, which we don't, right? Those are all zeros. That's what really matters. Okay, and over here, in this example, you've got a 4x4 matrix where all of the non-zero entries are all below, or either on or below the main diagonal, right? Here's some non-zero entries that are all on the main diagonal, but then all the other non-zero entries are down below it. And of course, we're allowed to have a couple zeros down here. We can have zeros wherever we like, but it's the non-zero entries that must be either on this diagonal or below it in order to be lower triangular. So this example is lower triangular. So just a couple examples just to reinforce the definition that we introduced on the last page at the end. Okay, and one note, this is a fact worth noting, a matrix is diagonal if and only if it is both upper and lower triangular. So think about that. If a square matrix is both upper triangular and lower triangular, what would that mean? Well, if it's upper triangular, all the non-zero entries have to be on or above the main diagonal. But if it's lower triangular, then all the non-zero entries must be either on or below the main diagonal. In other words, there's only one place that you're really allowed to have non-zero entries, and that's right on the main diagonal. So if that's the case, if all your non-zero entries are on the main diagonal, then next thing you know, you're a diagonal matrix. And that's the justification for this remark. Okay, a couple of observations. This is stated as a theorem, but I'm not going to prove this to you. A lot of these statements are fairly self-evident. Some of them are not so obvious, but all the same, I'm not going to prove them to you. Some of these you'll have to take on faith or try to prove them yourself as an exercise. For the first statement, what does it say? If U, so U is some matrix here, if U is upper triangular, then U transpose. So what happens if you take the transpose of a matrix whose entries are all on or above the main diagonal? For example, imagine if you want to try something concrete, take the transpose of this matrix. What's going to happen to it? It's upper triangular, but when you take the transpose, what's going to happen is you're actually going to end up with a lower triangular matrix now, because all the non-zero entries that were before used to be above the main diagonal are now going to be below the main diagonal. So if U is upper triangular, then U transpose is lower triangular. Okay, and then we have a similar result. If L, we're just using the letter L to represent the matrix that's lower triangular. If you have a lower triangular matrix L, then L transpose, well, that's going to be upper triangular. Okay, so that's the first observation. That's not too hard to see. This is less obvious, this next statement. But if you try it a few times, you start to just see why it happens. What happens if you take two upper triangular matrices and you multiply them? Well, it turns out that the product is going to be, again, upper triangular. So let's fill that in. And then if you multiply two lower triangular matrices, you might be able to just guess based on what the previous statement was. But it turns out if you multiply two lower triangular matrices, the result is going to be, again, lower triangular. Okay, and then what's our third statement? A triangular matrix is invertible if and only if all of, and then it stops suddenly. So we have to finish the sentence. It turns out that it's actually the same condition you would apply to test for invertibility of a diagonal matrix. Whatever the entries are that are not on the main diagonal, any non-zero entries that are not on the main diagonal, play no role in determining whether or not a triangular matrix is invertible. And that goes for upper triangular matrices and lower triangular matrices. Okay, so we have to just say if all of the diagonal entries, so the entries that are on the main diagonal, are non-zero. So that's how you can finish the statement C. For part D, so now we've got two more statements about the inverse of triangular matrices. So start with a lower triangular matrix. If you have an invertible lower triangular matrix, its inverse is going to be, again, lower triangular. And that's not obvious. That's not an obvious fact. But I'm telling it to you so you now know it's true. You can take it on faith or you can try to prove it, but I'm not expecting you to just be able to see why that's the case. It's a bit challenging to see why that's the case, but it is a really neat fact about lower triangular matrices. And you can probably guess that a similar result holds for upper triangular matrices. The inverse of an invertible upper triangular matrix is again upper triangular. Okay, so that's how we can finish those statements. So those are some properties about triangular matrices. A couple of examples. Here you have a 3 by 3 upper triangular matrix, and I stated that A, if I set it to be A, this is invertible. Now, why is that the case? How do we know that? Well, you can refer to statement C here in this theorem above. A triangular matrix, so this is upper triangular, so that counts as triangular, is invertible if and only if all of the diagonal entries are non-zero. Well, what are the diagonal entries? 1, 2, and 5. And since they're all non-zero, we know that this matrix is invertible. Now, notice that this statement doesn't tell you what the inverse is, but it does tell you that this matrix has one. Oh, I forgot to scroll up. Pardon me. So statement, I'm not sure how long I was off the screen, so I'm just going to repeat that last little bit. So pardon me if you've already seen me say this. So this statement said a triangular matrix is invertible if and only if all of the diagonal entries are non-zero, and this matrix is certainly triangular because it's upper triangular. So what are the entries on the main diagonal? We've got 1, 2, and 5, and those are all non-zero. So we know that this matrix is invertible. So that's why we can say this claim. But notice that this statement doesn't tell you what the inverse is. It only tells you that it does have an inverse. And that's still valuable because then you know that if you do want to go find that inverse, you know you will eventually find one because it does have one. So that is still information, but it doesn't go as far as to tell you what the inverse is. The other example here, we've got a upper triangular matrix B. This is not. So this one was invertible, but this matrix is not. And why is that? Well, the same reason. Use statement C, but in this case, note that the entries on the main diagonal are not all non-zero because we've got one of the entries here in the middle is actually equal to 0. Okay, so that's why this 0, if this were anything non-zero, then B would be invertible as well. But because there's a 0 here, this matrix is not invertible.